In the previous lecture, we studied solving nonlinear equations numerically. And we talked about a method for solving a nonlinear equation, which is bisection method. We now have another method, which is secant method. As we said, in this chapter, we studied 3 methods for solving a nonlinear equation. We finished bisection method. We now have secant method, and we will study another method, which is Newton's method. We studied these 3 methods in this chapter about solving a nonlinear equation. In secant method, we have this rule for finding the solution, for finding the approximate solution for the given equation. Secant method works on 2 points, 2 initial points. We must have 2 initial points for calculating or for finding the solution. We say xi plus 2 is xi, f of xi plus 1 minus xi plus 1 times f of xi divided by xi plus 1 minus f of xi. Here, x naught and x1 should be given in the question. In the question, x0 and x1 should be given, and you find x2. We always work on the last 2 values of x. We always work on the last 2 x values. Here, if x0 and x1 are given, we say x2, we find x2 from x1 and x0. x2 is x0 f of x1 minus x1 f of x0 dividing by f of x1 minus f of x0. This is how to find x2. After finding x2, we find x3. For finding x3, as I said, we always take the last 2 values of x. Here we have x1 and x2. The last 2 values of x are x1 and x2. We use x1 and x2 for finding x3. Here, to find x3, it equals to x1 times f of x2 minus x2 times f of x1 dividing by f of x2 minus f of x1. And then we have x0, x1, x2, and x3. The next x that we'll find is x4. To find x4 is, for finding x4, we use the last 2 values of x, which are x2 and x3. We use only x2 and x3 for finding x4. It is x3, sorry, it's x2 f of x3 minus x3 f of x2 dividing by f of x3 minus f of x2. Based on this rule, we write down these, okay? To find the next x is x5, okay? To find x5, we use x3 and x4. We always use the last 2 values of x for finding it. Here, x5 is x3 f of x4 minus x4 f of x3 dividing by f of x4 minus f of x3, and so on. We'll continue. We'll be continue until f of x, let's say n plus 2, means until the last x until the absolute value of last x is less than the epsilon. Epsilon is the error which should be given, or it may say it may the decimal points will be given. Okay, we may have the decimal points or the value of epsilon. Will we continue till we get the required value? Okay, here let's say if epsilon to be 0.005, will be continue until f of the last x is less than 0.005, or until the difference between the last two x values, or the difference between the last two x values is less than that value. No. Sorry? No. No. It doesn't take too much time actually. No, because here finding x's, x1, x2, x2, x3, x1, so on. In those, we just calculate this fraction. Okay, and for this, we have the function. We evaluate x values in the function and we plug it to this formula, you get the value of x. F of x should be, yeah, it must be given. The function must be given. Here, it's asking for finding the solution for a nonlinear equation. If the nonlinear equation is given, so what should you find? The function must be given. Look, in the questions, three things should be given. The function, the error, and the values of x0 and x1. These three should be given. And then we could find the approximate solution by using secant method. We now have an example, as you see. It says f of x is the sum of this function using secant method. The function is this. Here, it's impossible to find the solution of this equation analytically. So you must find it numerically. We need to find its approximate solution. The function is given, and the initial values, which are x0 and x1, are given. These are given. And also, it's given that do calculations correct to 3 decimal points. To 3 decimal points. So you must be continue until at f of x, let's say n plus 2. I mean the last x, until f of the last x is less than 4 point, as it says 3 decimal points or 5. We always use 5 for the first non-zero. Okay, or we will be continue until the difference of the last two x values means x n plus 2 minus x n plus 1 is less than this value. Okay, will be if any of these two satisfied, we stop there and we choose the last value of x. We say that's the solution for the equation. That's the approximate solution for the equation. Okay, the last value of x in which one of these two conditions satisfied. Sometimes both are satisfied. Okay, sometimes one of them is satisfied, so you should check both. Okay, if one of these is satisfied, we stop and we choose the last value of x that you found. We say it is the approximate solution for the nonlinear equation. For this equation, we need to first find x2 as x0 and x1 are given. X0 and x1 are given. We should find x2. We say x2 x2 is x1 f of, sorry, x0 f of x1. Yeah, it is x0 f of x1 minus x1 f of x0 dividing by f of x1 minus f of x0. We have to evaluate this. So for this, we need to find, or we need to evaluate the function at both x0 and x1. We have to evaluate the function at those two values. F of x0 is, if x0 to be 1, it is sine 1 plus 3 times 1 minus e to the power 1. We evaluate this. We get a value for f of x0. And we have to evaluate x1, the function at x1. x1 is 0. Okay? Here, it is f of 0, sine 0 plus 3 times 0 minus e to the power 0. This one is equal to -1. Okay? Sine 0 is 0. 3 times 0 is also 0. We have minus e to the power 0. And any value, e is a real number, 2.71 and so on. Okay? Yeah, it is an irrational number. Any value to the power 0 is 1. And you have a negative sign, which is -1. We also need to evaluate this. Then we plug these with x1 and x1 into the formula to get x2. We get an x2. Let me check if this calculated here or not. That's it. This is f of x0. This is f of x1. It's 1.232. Okay. Now to find x2, you say x2 is, let me check what's the value. 1.1232. x0 is 1. F of x1 is -1. Minus x1 is 0 times f of x0 is 1.232. Okay, dividing by f of x1 minus f of x0. F of x1 is 1. It's -1 minus f of x0 is 1.232. Okay, 1.1232. Okay. Yeah, that's it. We now calculate this. We get a value for x2. Okay, we get a value for x2. This equals to, this becomes 0, 0 times any value is 0. We get -1 dividing by -2.1232, which is 1/2.1232. As both numerator and denominator negative, it becomes positive and equals to 0.4710. This is x2. Then to find x3, we do the same. But instead of using x0 and x1, we use x1 and x2. As I said, we always use the last two x values to find the new x. Okay? We need to first find f of x2. F of x2 is equal to what? We replace x2 by 0.4710 in the given function. In the given function, which is sine x plus 3x minus e to the power x. We find its value. And it is, look, we plug it to here. We get This is 0.2652. This is f of x2. It's not less than 0.3005. Is it? So you'll be continue. We'll be continue. We do, or we find next x value. So the next x value is x3. We need to find x3. So here x3 is x1 f of x2 minus x2 f of x1 dividing by f of x2 minus f of x1. We now find x3. Okay, we find x3. Then we check if it satisfies the condition or not. If it's less than f of x, if f of x3 is less than the epsilon or the error, we stop. If not, you'll be continuing to find x4 and so on. You could also check if here x3 minus x2 is less than error. Even if this one is satisfied, we stop. Okay, that's it. Here it's done. Here this is x0, this is x1, sorry, this is x0, x1, x2 and x3. In x3, when we find it, after 4 decimal points we have non-zero values. Okay, after 4 decimal points we have non-zero values. And it says, sorry, the one before, look, we say absolute value of f of x. Okay, you always take its absolute value, even if it is negative, we don't care, we take its absolute value. Now here, this one, the previous one, this one, the absolute value of minus 0.0012, is it less than 0.3005 as it says for 3 decimal points? Is it true? No. So that's why x3 is found. That's why x3 is found. But x3 satisfies it. Even if you have any value after 4 decimal points, the first 4 decimal points are 0. You may have a non-zero decimal point after 4 zeros. So it's clearly less than 0.3005. As here, after 3 decimal points, we have a non-zero value. Okay, even if this, let's say 7, if there's 2, 3, any value after 4 decimal points. Here, if you have 4, let's say 8, is it less than 0.3005? Of course, it's less. So you stop. As it satisfies the requirement. Okay, as it's less than the error, we stop. That's it. This is how to find the solution. Look here, the last value of x. This is the last value of x. See, this is the approximate solution for the equation. For sine x plus 3x minus e to the power x, this is an approximate solution. This is an approximate solution. So it's a root for the, it's an approximate root for the equation. X. Yeah. Sorry, the last one is down. It's x1, x2, x3. This one is x. This is the last value of x. Okay. Yes. The x value should be the approximate solution, not f of x. F of x is near to 0. Okay. It's near to 0. We say the roots of an equation. The roots of this equation, let's say f of x equals x squared plus 1. And sorry, minus 1. What are the roots for this equation? It's 1 and minus 1. So if we evaluate the function at 1 and minus 1, it equals to 0. Okay, f of x is 0. Could you say 0 is a root? No, it's f of x. 0 is f of x. You say f of 1 is 0, and also f of negative 1 is 0. So these two values, 1 and negative 1, are both zeros for the function. These are exact solutions for the function. But some functions, like like those given in this example, it has no exact solution. We need to try to find an approximate solution. So the approximate solution is this value, as the function at this value is less than the error, means it is near, it's close to 0. We never get exact 0. Okay, so that's why we stop here. This value of x, the last value of x that you found, is the approximate solution for the given equation. We now have another example. In this example, it says find the approximate solution for this equation. It says find the root or find the solution for this equation. It's a nonlinear equation. And here both x0 and x1 are given. x0 is 0 and x1 is minus 0.1. And it says error is epsilon is 0.0005. We must get that. Here we will be continued an iterative method. We must be continued until f of x, the last value of x, let's say xn plus 2, is less than, I mean, it's in absolute value is less than 0.0005, or if xn plus 2 minus xn is less than 0.0005. If one of these two conditions satisfied, we stop. Okay, we stop of these, one of these two conditions satisfied. Now, all the required information are given. The function x0, x1, and also the error. These all are given. So we do the same as you did before. We do the same as you did before. In the first iteration here, x0, x1. Okay, that's x0, x1. We find x2. That's the value of x2. The epsilon value of this is, of f of xn plus 1 is this one. It's not less than 0.0005. Here epsilon is 0.0005. We must get that this one is less than that value, or this less than that value. One of these. Sometimes both are satisfied at the same iteration. In the second iteration, we use these two. We always take the last two x values for finding a new x. To find x3, we use those two. These are x1 and x2. We evaluate x3 in the rule. The formula is x0 f of x1 minus x1 f of x1 divided by f of x1 minus f of x1. That's for the first iteration to find x2. And then for finding x3, x1, so on, we just use the last two values of x and applying the same formula. Here, this is x3, this is x2, this is x3, x4, x5, x6, x7. Okay? At this value, okay, at this value, we get that 0.0003, but the previous one is not less. Even this one, in both, this one is not less than that. As we have 0.0006, it is greater than 0.0005. And even here, 0.0016 is greater than the error. So you will be continue. We stop if one of these two is less than the error. Is less than the error. So in the next step, we get that 0.0002, 0.0002, yeah. And here, we say it is less than the error. So you stop. And also here, this is less than. Even if only one of them satisfied, we stop. Okay? If only one of them is satisfied, we stop. Yeah, just want to see that. But it's better to do both. This one becomes less than the error before that one. If you do this one, so you may have extra steps. So do both. Always, look, always make this table in second. Make this table, the same table. And find both f of x n plus 1 in an absolute value. Make these two columns also. Any of these two is less than the error, stop. Stop at that iteration. And choose the last value of x. The last value of x is this one. So this one is the solution for the given equation. The last value of x is the approximate solution for the given equation.
What about if x is less than the given absolute error? X then plus 1 minus x is not.
So you stop. I said if one of these two conditions satisfied. I didn't say both. Okay?
And the other one,
Even if only one of them is satisfied, we stop. Okay? Look at the previous example. Here, this is f of xn plus 1. Okay? Can you say the difference of these two is less than 0.305? No, it's not. Look, it's not less. Even that's not less than, but we stop. As one of these is satisfied. So it's better to calculate both. Any of these gets less than the error, stop at that iteration. Don't care about the other one. This is about second method. So as I said, we choose the last value of x. This one is the approximate solution for the given equation. Sometimes it's asking for finding of find x values for 3 iterations. So you just need to do 3 iterations. This is the first iteration. This is the second. This is the third. You don't need to do others. If the number of iterations is given, just do the same number of iterations which is given in the exam, in the question. If it's not, if it says find the rules, find the solution, or find the approximate solution, you should do the same as we did now. You should be continued until you get that either this or that one is less than the error. Okay? This is about second method. Any questions? This is an iterative method. All of these 3 methods are iterative methods, means steps after each others. Okay? We have some steps for solving or for finding the solution of any nonlinear equation in some steps. So in some iterations, in all bisection methods, secant method, and also Newton's method. We now have Newton's methods. The rules are given in exams, but for bisections not. Bisection is adding both endpoints, dividing by 2. It's not given. It's not a rule. It's not a formula actually. Okay? But here, these rules, based on the previous year's final exams, the rules are given. Okay? and I'll provide you the list of rules that will be given for the final. Okay. Now we have another method for solving a nonlinear equation, which is Newton's method. Newton's method. Newton's method. Let's take a break. But sorry, if don't go out. We now have another method, which is Newton's method. It's the last method in this chapter. In this method, we do the same. We are going to find the approximate solution for a given nonlinear equation. Newton's method works on only one initial value. We only need one initial value in Newton's method. The rule is this one. For finding each next x value, we use the previous one. For example, if you have given, if you have xn, to find xn plus 1, as xn minus f of xn dividing by f prime of xn. F prime of xn means derivative of the function, evaluating derivative of the function at the given value. Okay, so here the initial value must be given. Then let x naught is given and f of x is given also. To find x1, x1 is x naught minus f of x naught dividing by f prime x naught. Then for finding x2, it's the same formula, but we always use the last x value. The last x value is x1. We need to find it for finding x2. It is x1 minus f of x1 dividing by f prime at x1. Then for each x, we use the previous one. And we use the same rule, the same formula, which is xn plus 1 is xn minus f of xn divided by f prime of xn. But here, you have to first find the derivative of the function. You should know how to find the derivative of a function. Okay. And so, two successive x values, the absolute value of their difference is less than epsilon, or f of the last x value is less than epsilon. If one of these is satisfied, we stop. Yeah, only the formula is different from the second method. The procedure is the same. Here we have this example. It says use the Newton's method to estimate the root of this function. Employ an initial guess. X naught is 1. This is x naught. We must have x naught. We must have the initial value. In Newton's method, we just need one x value. But in second method, we need two x values, which are x naught and x1, to find x2. Okay, but here in Newton's method, we could find each x value from the previous x value. So you just need one x value at the beginning. So here the initial value for x naught is 1. This is given. We just need one initial value for x. It says do calculation in 5 decimal points. Means we should be continue until all points. That's 5 zeros, then 5. And obtain the solution equal to the sorry, it says do the calculation for 5 decimal points. It doesn't mean that. Here it says take 5 decimal points in your calculations. Means when you find f of, let's say, x naught, take 5 decimal points take 5 decimal points. So the results should be given in 5 decimal points. For example, if you have, let's say, 2.358218728. So we just take the first 5. But you have to round it. It becomes 2, is it? The last one becomes 2. So that's it. So you should round it to 5 decimal points. The results should be rounded to 5 decimal points. And it says a solution to 3 decimal places. Okay, accurate to 3 decimal places. So the error is 0.305. This is error. No, it says 3. This is not true. This should be 3. No. No, look. I'll do calculations in 5 decimal points. Okay? For example, if you find 2 successive x values, let's say if x1 to be 0.9678121, okay, and x2 to be how many decimal points we have? 1, 2, 3, 4, 5. So we don't need to take the others. We need to write down 5 decimal points for our results. Okay, we need to write down 5 decimal points for our results. The second one to be 9, 6. Let's see, 2, 8 is 5. These are 2 x values, and each are written in 5 decimal points. For each, we have 5 decimal points. If the difference of these 2 is less than 0.0005, we stop. We should stop there. Yeah, actually, it is 3 decimal points. Just 3 decimal points. But you should write down the results for 5 decimal points. You should take 5 decimal points for your results. We may have many decimal points. You should take only 5 of them. Okay? You should take 5 decimal points for each result. Once you get that x1 minus x2 or x2 minus x1 in an absolute value is less than this, we stop. Or if f of the last x is less than the error, we stop. Okay? The error is this one. That's it. The error is 3 decimal points. It says 3 decimal points. That is the error. Clear? But this one is given as 4 decimal points, so it's not true here. Error here, it is only 3 decimal points. Okay? It is 3 decimal points. Now, we need to first find the derivative of the function as we need it in the formula. Okay? Write down the formula first. We say xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Okay? We use this formula. In this formula, we need one x value and both f and f prime. F is given, which is x cubed minus sine x. It's x cubed minus sine x. We need to find its derivative. Its derivative is f prime of x is, derivative of x cubed is 3x squared. Then minus. Derivative of sine is cosine. You have to know this. Okay? You have to know how to find the derivative of those functions. derivative of sine is cosine. This is derivative of the function. We now use f and its derivative to find the next x value. If the first x value, which is given, which is the initial one, it's x naught, is 1. To find x1 is x naught minus f of x naught dividing by f prime of x naught, which equals to, what's x naught? X naught is 1. It's 1 minus f of x naught. We replace each x in the function f by x naught. x1 is 1, which is 1 cubed minus sine 1, which is still 1 minus sine 1. Dividing by its derivative at the initial value. Derivative is 3x squared minus cosine x, which is 3 minus 3 times 1 squared is still 3, is it? Times cosine 1. Now evaluate it. Okay, evaluate. You get the result, which is, that's it. It is 0.93555. Look, 5 decimal points are given. Okay, 5 decimal points are given. It's not given like to say 0.93. Okay, here we have 2 decimal points. So you should write down 5 decimal points for your results, as it's asking in the question. This is x1. How about x2? To find x2, it is x1, which is this value, minus f of x1 dividing by f prime of x1. We need to find f of x1 and f prime of x1. We replace each x in f and f prime by this value, 0.93355. We replace each x in both functions, f and f prime, by x value. Here, in finding x2, we use x1. So we have to have the evaluation of both functions, f of x and f prime of x at x1. We need to find them, which is this value here. This is f of x, and we should find f prime of x. Okay, f prime of x, we find it. We said f prime of x is 3x squared minus cosine x. To find f prime at 0.93555 is equal to 3 times 0.93355 to the power 2 minus sine of this value of 0.93355. Evaluate, calculate it, and you get f prime. Then, like all x1, f of x1 and f prime of x1 in the above rule, in this rule, to get x2, f of x2 is less than the epsilon, or x2 minus x1 is less than epsilon in an absolute value. We say we stop at that step. Here, x0 minus x1 is this value. Okay, it's greater than the error. Yeah, it should be. Let me change the above one actually. This one, write down for 4 decimal points. Change this to 4. Okay, change that one to 4 because it's calculated for that. Change this to 4, the above one, this one. Then we say it is not less than the error, so you should continue to do next iteration. We need to find x2. That's it. This is x naught. This is f of x naught, and this f prime of x naught. This is x2. This is x3, x4, x5, and so on. Look, if the difference between two successive x values means the absolute value of x2 minus x1 is less than epsilon, or f of the last x in an absolute value is less than epsilon, less than the error, we stop the iteration and we say the last x value is the solution. The last x value is the solution. Here, as you see, this is f of x. This is f of xn, and this is 0 actually. This is f prime. Here, the difference between two successive x values, the difference between two successive x values is 0 here. It is 0. Okay? So the last x value, even the previous one, as it equals to 0, the previous one is the same. It is the solution. The difference between these two, both are the same. Their difference is 0. It's less than 0.4 followed by a 5. Of course. Is 0 less than 0. Sorry. Can you say 0 is less than 0. It's true? Of course, it's true. 0 is less than that value. It's a positive value. All the positive values are greater than 0. So this is true. We stop here. We stop here. Even this one. Look, for the previous one, it's 0.0015. It's 0.0015. 0. Is it true? No. As you have triple O's, then 15. But in the right hand side, we have 4 O's followed by a negative non-zero value. So this one is not less than. This one is not less than that value. So that's why we need to do another step. We need to do another iteration. Yeah. At this step, we have to find next iteration. We have to find the next iteration. This is f of x in the next iteration. This is f of x3. This is f of x3. Is it less than that value? Here you have 0.4, then 1. In the right hand side, you have 0.4, 5. Which one is bigger? Of course, the error is bigger. So we get f of x, which is less than the error, less than the absolute error. So you stop there. Even you don't need to do this step. Even you don't need to do this step. As you get the same x value for the solution, for the approximate solution. As you see here, these two x values are the same. We see the last x value is the solution. If we don't do this step, what's the solution? The solution is 0.92862. Whatever you do the next one, it's the same. Okay? It's the same value. X value is the same. So that's why we could stop here in the previous step. We could stop in the previous step here. We don't need to do this step. Look, in the previous step, we say these two x, the difference of these two x is not less than the error. It's not less than the error. We said if one of these two satisfied, we stop. If f of the last x is less than the error, or the difference between two successive x values is less than 0. In the previous step, only one of the conditions is satisfied. So even you could stop there, okay? But here, this is worked on the difference of two successive x values. If we look at this one, you could stop there. You don't need to do the next step. So this is an extra step, actually. The last one is an extra step. You don't need to do that. Even if you do it, you get the same result. So why do you do that? You don't need. So the last value of x is the solution, as the approximate solution for the given equation. We now have Newton's method for special functions. If you have x to the power n minus c to be 0, to find the approximate solution for this equation, if we have, let's say, x squared minus 4 equals 0, it's easy to find. It has an exact solution, which is minus 2 and 2. We could solve it. You could factorize it and solve it. Or you could say x is square root of 4, which is plus minus 2. We get two x values, which are plus 2 minus 2. But in this one, let's say x squared minus 6 equals 0. How about this one? Here, x is square root of 6. We cannot evaluate, okay, without using calculator. What we do, we need to use Newton's method. We need to use Newton's method. Here, we say we let f of x to be this function. We let f of x to be that function. That's it. This is the function. We let f of x to be this function. Then its derivative is, this is c, which is a constant. It's 0. Derivative of this function, k is a power. Okay? It's an exponent of x. We say it is, we bring it to front and we reduce the exponent by 1. Is it? So we get k times x to the power k minus 1. This is f prime. This is f prime. We now have f and f prime. So what's the Newton's method? We say xn plus 1 is xn minus f of xn dividing by f prime of xn. We use this function here and we use this function. That's all. So this equals, they're the same. Yep, the same. But instead of giving f of x to be this function, this should be, this is given, okay? It's given as an equation like this, okay? So that's it. In this lecture notes, it's reduced to this function. It's actually don't need to reduce, okay? You could just use this one. You could just use this one. Use this one for solving the problems. Here, it says use Newton's method to locate the root for this function. Use the initial guess x naught to be 1 and iterate until this error is 0.005. We must be continue until f of xn plus 1, let's say, is less than error, or xn plus 1 minus xn is less than the error. One of these must satisfy, then we stop. Okay? What we do, this is f of x. Then we find its derivative. And we evaluate. This is the rule. This is f of x and this is f prime of x. Xn here. This is the reduced one, we could use this one also. You even don't need to do this one, okay? Because it is reducing the above one. Here, 2 is took as common and simplified more. You even could use this one. We are familiar with dealing with this formula, so use it. You don't need to reduce to the previous to this one, to the below one. We need to find xn plus 1. So x1 is x naught minus f of x naught dividing by f prime of x. We find x1. Okay, this is x1. Then to find x2, we use x1. We plug x1 to the function, to the formula to get x1. It's the same actually as we did before. Here, the reduced form is used. Okay, we don't need to use that form of the formula. Here for this x1, we need to find f of x1, which is 0.25. Is this less than 0.005? No. Oh, is 1 minus 0.25 less than epsilon? Epsilon is 0.005. No, none of these satisfy the condition. So yeah, we need to be continued. We need to be continued. Then we continue to 2 steps, 3 steps, 3 iterations. In the first iteration, x1 is 1, x2 is 1.5, f of xn plus 1, which is f of x2, is 0.25, so which is not less than, this is not less than 0.005. So that's why we need to do another iteration. In the next iteration, we have this one. This is x1. Then we find a new x. We find f of the new x, which is 0.007. 0.007 is not less than 0.005. Okay, and 7 is greater than 5. Here we have the same number of decimal points. Okay, decimal points with 0, and the first non-zero decimal point in the here is 7 and here is 5, so that's why it's not less. Then we need to do another step. In the next step, we get that it is less. We get that this one is f of xn plus 1, which is less than 0.005. As you have 4 decimal points, the 4 decimal places are 0, then we have a non-zero value here. But here we have only 2 decimal places, so it's less than the error. So we stop. This x value is the solution. It is the approximate solution for the function. The function is x squared minus 2. This is f of x. So at this value, the function is close to 0. It is a root. It's an approximate root for the function. May not make the function to 0. Okay, may not be the exact 0 for the function, but the function at that value is close to 0. Okay, at this value, at the last x value, the function is close to 0. So that's why we say that value is the approximate solution for the function, which is x squared minus 2. Okay, this is the end of this chapter. So now we now have a new chapter, which is chapter 7. In this chapter, we talk about eigenvalue problems. Here we have only 3 topics. We have only 3 topics. Yeah, we just have 3 topics in this chapter. In this chapter, we study Grigorian circle theorem, then power methods, and one more, I think. Let me check. We have shifted power methods. We just have these three topics. In this chapter, we have three topics, which are Grigorian's circle theorem, power method, and shifted power method. Before we start to talk about those three topics, we should know what's an eigenvalue, how to compute it, okay? And how to compute the eigenvectors corresponding to the eigenvalues. And you also need to know the relationship between eigenvalues and eigenvectors. Here, we say, let A be an n by n matrix. We could find eigenvalues and eigenvectors for an n by n matrix. We could find it for a square matrix. For a square matrix, we could find eigenvalues and eigenvectors. Here, we say let A be a square matrix. Be a square matrix. We say A times B is equal to lambda times B. Here, V in both, V is the eigenvectors, corresponding to lambda. For each eigenvalue, we could have an eigenvector. For each eigenvalue. Here, lambda is used for, this symbol is used for eigenvalues. Eigenvalues are denoted by lambda. We say, for matrix A, after finding the eigenvalues and eigenvectors, after finding eigenvalues and eigenvectors, if we multiply the matrix by the eigenvector, a matrix by an eigenvector is equal to the eigenvalue multiplying by the eigenvector. Okay, it is the eigenvalue multiplied by the eigenvector. As we said, if we have lambda 1, so for this lambda 1 is an eigenvalue. For this lambda 1, we could find an eigenvector, sorry. We could find an eigenvector, V, to be the corresponding eigenvector to lambda 1. We say A times B, let's say it's V1. A times V1 is lambda 1 times V1. Okay? Sorry. For lambda 2, if lambda 2 be another eigenvalue, let's say it's lambda 2. For this lambda 2, we'll talk about this, how to find the eigenvectors. Okay? V2 is the eigenvectors corresponding to lambda 2. Then we say A times V2 must equal to lambda 2 times V2. And then for V3 and so on. The number of eigenvalues and eigenvectors depend on the size of the matrix. For a 2 by 2 matrix, we just have 2 eigenvalues. And as we said, for each eigenvalue, we could get an eigenvector. So we must have 2 eigenvectors also. Okay, for a 2 by 2 matrix, we must have 2 eigenvalues and 2 eigenvectors. And for a 3 by 3 matrix, we must have 3 eigenvalues and 3 eigenvectors. For each eigenvalue, you could get an eigenvector. We'll talk about how to find eigenvalues and eigenvectors later on. Here, we have given this example. In this example, a matrix is given and it is eigenvector is given. For this, to find the eigenvalue, corresponding to this one. How to find it? This is V and this is A. We say V times A must equal to lambda times V. Here lambda is a noun. We need to find it. We need to find it. We say A times V must equal to lambda times V. This is V and that's A. We first multiply A and V. A is -6, 3, 4, 5 times V is a vector. Eigenvectors are always a vector. Eigenvalues are always scalars. Eigenvalues are values, only one value. Okay, it's not a vector or a matrix. It's a scalar. It's 1, 4 here. It is A times B. Let's multiply these two. And what we get? In multiplying these two, we get 6 minus 6 plus 12 is 6. And then 4 plus 20 is 24. So A times B is 24. A times V is 24. Sorry, it is 6 and 24. It is that vector. In the above rule, we said it equals to lambda times B. Lambda times V. What's V? V is given with 1 and 4. Let's replace V by the vector. What's the value of lambda here? We compare these two. If we take 6 as common in the left, what we get? I'm writing down here. If we take 6 as common in the left, we get 6, 1, 4 is equal to lambda times 1, 4. So what's the value of lambda? It is 6. So lambda is 6. If we multiply V by 6, we get 8 times V. So lambda here is 6. Lambda is 6. To find lambda, to find eigenvalues and eigenvectors, we'll talk about these. Here, we say let A be a square matrix of dimension n by n. This is an n by n matrix. It is 2 by 2, 3 by 3, 4 by 4, or any n by n matrix. And let V be a vector of dimension n. The multiplication of them is also dimension n. Okay? As we did above, we multiplied the matrix, which is 2 by 2, by a 2-dimensional vector. We get a 2-dimensional vector. Okay? The result is a 2-dimensional vector. And what if you have a 3 by 3 matrix multiplied by a 3-dimensional vector? The result is a 3-dimensional vector. Okay? And for 4, 5, and so on, for all are the same. Here it says, let A be an n by n matrix. So it's an n by n dimensional matrix. And V be an n dimensional vector. So the multiplication of them, A times B. A is n by n. And this is n dimensional vector. Multiplication of them is a vector of n dimension. Okay? It is an n dimensional vector. The multiplication of these two is an n dimensional vector. It is written here. These are nothing actually. Okay. Now, to find eigenvalues and eigenvectors, we say we need the identity matrix. We studied identity matrix in the first chapter. In the first chapter, we studied an identity matrix. We take the identity matrix based on the given matrix. If it says find the eigenvalues and eigenvectors for this matrix, if the size of the given matrix of matrix A, if it is 3 by 3, we must get the identity matrix for a 3 by 3 matrix. Okay, so I must be a 3 by 3 matrix, which is 1 0 0 0 1 0 0 0 1. Okay, if A to be a 2 by 2 matrix, so I must be a 2 by 2 matrix. Okay, the size of the identity matrix must be the same size as the given matrix. Okay, both must have the same size. Then we say AV is equal to lambda IV, lambda IV. Okay, moving this to the left, we get AV minus lambda IV. If we take V as common, we get A minus lambda I times V. Okay, we equal this. V is a vector, is an n-dimensional vector. For example, if you have, let's say A to be a 2 by 2 matrix. Let's take a matrix. A to be 1 3 4, let's say 5. Then A minus lambda I V is equal to A minus lambda I. V is two-dimensional vector. It is, let's say, V1, V2. It must have two components, as you have a 2 by 2 matrix for A. As A is a 2 by 2 matrix, so the vector, the eigenvector, must have two components. If A is a 3 by 3 matrix, so the eigenvector must have three components. If A is a 4 by 4 matrix, the eigenvector must have 4 components. Okay, it depends on the size of the matrix. So this is a linear system actually. This is a linear system. A minus lambda I multiplying by V1, V2 is a linear system. The solution of this linear system, is values of V1 and V2. So by solving this linear system, we get the eigenvalues. We get the eigenvectors. We get the eigenvectors by solving this linear system. Then to find the eigenvectors, the eigenvalues, here we say for this linear system, A minus lambda I must be singular, means its determinant is 0. Its determinant is 0. This one, the coefficient, this part. A minus lambda I, its determinant must be 0. The determinant of A minus lambda I must be 0. Okay, it must be 0. That's it. From this, here we get an equation. We get a polynomial actually. We get a polynomial of degree n based on the size of the matrix. If it's a 2 by 2 matrix, you get a polynomial of degree 2. If it is a 3 by 3 matrix, you get a polynomial of degree 3, and so on. We solve that polynomial, we get the eigenvalues. After finding the eigenvalues, you could compute the eigenvectors easily. It's easy to compute the eigenvectors. It's just solving a linear system, nothing else for finding the eigenvectors. Here, let A be, let's say, 2, 1, 8, let's say 5. To find the eigenvalues here, the eigenvalues is the roots of the polynomial of the polynomial that we get from A minus lambda I. We need to first find lambda I, and A is given. We subtract lambda I from the matrix, then we find its determinant. That we equal the determinant to 0, then we solve it. The values of lambda will be the eigenvalues. Let's do it. What's lambda I? Lambda times I. As A is a 2x2 matrix, so I must be a 2x2 matrix. It's 1, 0, 0, 1. So lambda I is lambda 0, 0, lambda. Okay? This is lambda I. We subtract this from A. We subtract this from A. So determinant of, let's first find A minus lambda I. And then we find its determinant. A minus lambda I is equal to, this is A, and this is lambda I. It is 2 minus lambda. We just subtract these two corresponding elements, entries. It's 2 minus lambda. Then 1 minus 0 is still 1. 8 minus 0 is 8. 5 minus lambda is 5 minus lambda. This is A minus lambda. We now find the determinant of this matrix. We now need to find P of lambda. P of lambda is the determinant of the matrix. P of lambda is, determinant of this matrix is 2 minus lambda times 5 minus lambda. Here, to find the determinant, we multiply these two minus multiplying these two. We studied this rule. Okay? The minus 8 times 1 is 8. We now need to multiply these two brackets and simplify it. It becomes 10 minus 2 lambda minus 5 lambda plus lambda squared minus 8. This equals to lambda squared minus 2 lambda minus 5 lambda is minus 7 lambda. 10 minus 8 is 2. This is the polynomial. We find the roots of this polynomial. The roots of this polynomial are the values of lambda. The roots of this polynomial are the eigenvalues. And the roots of this polynomial are the eigenvalues. Okay? This is how to compute the eigenvalues for a 3x3, 4x4 matrix. It's the same procedure. It is the same procedure for any size of matrix. Here we have another example. It says, find the eigenvalues for this matrix. What we do, we say, we need to find the determinant of A minus lambda I. This is A minus lambda I is lambda 0, 0, lambda. Is it? As it's a 2x2 matrix, so I must be a 2x2 matrix, and multiplied by lambda, we get this one. Yeah. Just a moment, we will talk about it. Then 3 minus lambda minus 2 minus 0 minus 1 minus 0, 5 minus lambda. We get that matrix. This equals to, so A minus lambda I is 3 minus lambda, then minus 2 minus 0 is minus 2. Minus 1 minus 0 is minus 1. 5 minus lambda. Find the determinant of that matrix. That will be P of X. Okay? That will be P of X. The determinant is multiplying these two, then minus multiplying these two. We get this polynomial. After simplifying, we get this polynomial. The roots of this polynomial are the eigenvalues. They are lambda 1 and lambda 2. Okay? This is how to find the eigenvalues. For a 3x3 matrix, it's the same. A minus, sorry, here you have B minus lambda I. Here B minus lambda I. B minus lambda I is equal to this one minus lambda I is lambda 0, 0, 0, lambda 0, 0, 0, lambda. We take a 3 by 3 identity matrix and multiply it by lambda. We get this. Now subtract it and then find its determinant. Subtract it and find its determinant. Subtracting, we get this one. Then find the determinant of this matrix. We could use any method for find its determinant. And we studied how to find the determinant of a matrix in chapter 1. The determinant of this matrix is P of lambda. Is P of lambda. That's it. The roots of this polynomial, is the roots are the eigenvalues. Here we have 3 eigenvalues. For a polynomial degree 3, we have 3 solutions. In the above one, for a polynomial of degree 2, how many solutions do we have? 2. For 3, we have 3. So it depends on the size of the given matrix. The given matrix here is a 3 by 3 matrix. So we must have 3 eigenvalues. Okay? In the above one, the size of the matrix is 2 by 2 matrix. So that's why we have 2 eigenvalues. Okay. Here it's the same actually. It's what I said. To find the eigenvalues, this is the procedure. Find the coefficient of the characteristic polynomial. Find its roots. Here, this means find P of lambda. Find P of lambda. And then find its root. Find its roots. The roots become the eigenvalues. Okay? The roots become eigenvalues. And then to find the eigenvectors, for each lambda, we replace each here. Okay? Then we solve it. We get the components of B. It will be the first eigenvector. Then for the second eigenvalue, we replace here. We get another B. That will be second eigenvector. Let's take an example here. Let's say, let me take an example. And let A be this is 0, 3, 2, 1. Okay. This is a matrix. Okay. First, we need to find eigenvalues. You must first find eigenvalues, then you could find eigenvectors. As the eigenvectors depend on the eigenvalues. For each eigenvalue, we could find an eigenvector. Okay. Here, for this one, to find the eigenvalues, we need to find the determinant for eigenvalues. Are the roots of this determinant, P of lambda, sorry, are the roots of P of lambda, which equals to determinant of A minus lambda I. We need to find the determinant and find the roots. That will be the eigenvalue. For eigenvectors, for finding eigenvectors, what we do, we say A minus lambda I times B equals 0. Solve this system to find V corresponds to lambda. For each lambda, we could find a V. Okay? This is a system. It's a system. Let's solve this example. So that's all what about eigenvalues and eigenvectors here. What's the eigenvalues? We must first find eigenvalues. We say P of lambda. First, let's find A minus lambda I. A minus lambda I is 2301 minus what's lambda I? It's 1001. Yeah, lambda. Yeah, lambda 00 lambda. It's lambda times a 2 by 2 identity matrix. A 2 by 2 identity matrix is this one. If we multiply it by lambda, we get lambda 00 lambda. Okay, lambda 00 lambda. We now subtract it from matrix A. This equals to 2 minus lambda, then 3 minus 0 is 3. 0 minus 0 is still 0. 1 minus lambda. Okay. Now we need to find its determinant. Its determinant is multiplying these two minus multiplying these two. So determinant of A minus lambda I is 2 minus lambda times 1 minus lambda minus 0. 3 times 0 is 0. That's why you don't write down. Okay? Minus 0 lambda. Now, this is P of x, P of lambda, sorry. P of lambda is 2 minus lambda times 1 minus lambda. We don't need to expand it actually, as it is only, as it's factorizing. We need to solve it, okay? But in the previous one, as you have, let me go up here, down. We have this extra term, that's why we need to expand it, then solve it, okay? Then solve it. But for this one, we don't need. So lambda one is what? It's 2. And lambda 2 is 1. You may say lambda 1 is 1 and lambda 2 is 2. It's not a problem. Okay? Doesn't matter. Which one do you choose for lambda 1 and which one do you choose for lambda 2? Okay? That's it. Lambda 1 is 2 and lambda 2 is 1. Here we have both eigenvalues. We got their eigenvalues. These are the eigenvalues. Now, we need to find an eigenvector for each of these two eigenvalues. What we do, we need to solve this linear system. We say A minus lambda I times B equals 0. This is a homogeneous linear system. Then, what's A? A is given. A is 2301. 2301 minus what's lambda I? Lambda, let's find it for lambda 1. For lambda 1 and then for lambda 2. We have to do the same procedure for both. Minus. If we multiply an identity matrix by 2, here lambda is 2. Okay, as we are going to find the eigenvectors for lambda 1. Okay, it is 2002. Okay, times V. The size of A, the size of A is a 2 by 2 matrix. So V must be, let's say, V1, V2 equals 0, 0. That's a system actually. Okay, it is a system. Now we subtract these, we get 2 minus 2 is 0. 3 minus 0 is 3. 0 minus 0 is still 0. 1 minus 2 is minus 1. Times V1, V2 equals 0, 0. We now multiply these two. We get V3, V2 equals 0 and minus V1 equals 0. How about V1, V2? What are the values of V1, V2 here in these two equations? In the first equation, we get that V2 is 0. In the second, we get that V1 is 0. Means the eigenvector corresponding to this eigenvalue is 0, 0.
Then isn't it always you?
No, it could be not 0, yeah. We have many examples which is not 0. It could be complex number, it could be a non-zero real number, it could be negative, it could be positive, any value. But in this example here, it is 0. Okay? Here it is 0. Now, the eigenvector corresponds to lambda, which is 2, is 0, 0. This is for the first one. How about the second one? We do the same. We do the same, but we use lambda 2, which is 1. Lambda 2 here is 1. Let's do it. Let me check what's A is 2301. Here we say for lambda 2, which is 1, A minus lambda I times V is equal to 2301. It is 2301 minus lambda I. Here lambda is 1. Lambda is 1. 1 times identity matrix is still the identity matrix. Times V. Let's say name it by A1, A2. Choose different symbols for each for different eigenvectors. This equals to 0, 0. Now we subtract this from the matrix A. This equals to 2 minus 1 is 1. 3 minus 0 is 3. 1 minus 0 minus 0 is 0. It's 0. Times A1, A2 equals 0, 0. So we get that A1 plus A2 equals 0. Okay? And the second equation, both are 0. If you get something like this, choose any value for one of the components. Choose any value for these two components, one of them. Yeah, 3A2, sorry. Choose any value, any real value for A1 or A2, for one of them. Let's say if A2 to be 1, may someone else choose any other value. Let's say may someone else choose A2 to be 5, A2 to be 2, A2 to be 8, A2 to be any value. Okay? Let A2 to be, let's say, 1. So how about A1? Is it? A1 is minus 3. May someone else choose a value for A1? You could choose any value for A1 and finding A2. Both are possible. Okay? So here we got values of A1 and A2, which is 1 and negative 3. Sorry, negative 1, negative 3 and 1. This is the eigenvector. Corresponds to this eigenvalue. That's how to find the eigenvectors. That's so good, as there's this case actually by choosing the value for one of the
It's for lambda two.
-3 and 1. A1, A2. Yeah, that's it. What if this is in the case if you have only one or two, if you have the number of equations less than the number of variables, you choose a value, one of them, and find others. Okay? What if you have the same number of equations and variables? For example, if you have let's say 3a1 minus 2a2 equals 0, and a1 plus 3a2 equals 0. In this case, you have to solve it. You have to solve this system. And you could use any method. Okay? You could use elimination, substitution, Gauss elimination, Gauss-Jordan, grammar rule. Did you study grammar rule? No, you haven't studied. Inverse, LU decomposition. Any of these methods could be used for solving this system. But the easiest one is substitution or elimination. Okay, solve these two equations simultaneously to get the values of A1 and A2. But in the case, if you have only one equation and two variables, you could choose a specific value for one of the components and find the other one, like what we did here. Sorry?
Any value is fine.
Any value, yeah. You could choose any value. This is how to find eigenvalues and eigenvectors. Okay? First, find the eigenvalues. Then for each eigenvalue, find the eigenvector. As you see, we obtain this eigenvector and this eigenvector. We obtained these two eigenvectors as we had two eigenvalues. Here we have a theorem, and this theorem says let A be an n by n matrix, and let lambda I to be to be 1 up to n. Here, as you have an n by n matrix, so you must have n eigenvalues. Lambdas are the eigenvalues. So you have lambda 1, lambda 2, lambda 3, up to lambda n. Okay? We have these lambdas. Then the eigenvalues, these are the eigenvalues for the matrix. We say the sum of all eigenvalues, must be the sum of all main diagonal entries. Let's return to the above one. Here we had two eigenvalues, which are 2 and 1. Okay, these are the eigenvalues. The sum of these two eigenvalues must be the same as the sum of these entries. Are they the same? Yeah. Must be the trace. It's called trace. Sum of elements on the main diagonal called trace. So the sum of all eigenvalues is equal to the sum of all entries on the main diagonal. And also the multiplication of all eigenvalues, is equal to the determinant of the matrix. In the above one, we said, let me check, 2301. بس او ما اساسين سر بابته او انما او طاي سبريك ولكن بيخم. Okay. Here we have 2301. This is matrix A. The eigenvalues, lambda 1 is 2, lambda 2 is 3. We said the sum of these two eigenvalues must be the same as the sum of these elements. And also, the multiplication of these eigenvalues means lambda 1 times lambda 2. This is the second rule. Is equal to the determinant of A. Let's check. Lambda 1 times lambda 2 is 2. Is it? 2 times. Determinant of the matrix is 2 times 1 is 2. Minus 0. Still 2. 2. It is 2 minus 0, which 2. So both are the same. These two rules are really important as we use later. We use them later for finding if in some cases we could evaluate an eigenvalue, and we should use one of these two rules to evaluate the second eigenvalue or the others. Okay, for evaluating the other eigenvalues or to compute the other eigenvalues, we use these rules. So now let's take a break, okay, for 10 minutes. Let's start our lecture again. We now have Grigorian's theorem, circle theorem. In this theorem, we just find the region which includes all the eigenvalues. Okay, we just find the region for the eigenvalues. Okay, in Grigorian's circle theorem, we don't find the eigenvalues themselves. We just find a region which contains all the eigenvalues. Here, we say let A be an n by n matrix, and BI, it's B1, B2, B3, depends on the number of eigenvalues. For each eigenvalue, we have a region. Okay, for first eigenvalue, for lambda 1, we have B1. For lambda 2, we have B2. For lambda 3, we have B3, and so on. B1 denote the disk in the complex plane with center at AII. AII, here, if B, for lambda 1, let's say, we have B1. So what's AII? AII is A11. It is A11 entry from matrix. This is taken from matrix A. It's the center of the circle, center of the disk. And radius is Ri, it's R1. So for lambda 1, we need to find B1. B1 is a disk, it's a circle, okay? Which its center is A11, okay? And the radius is, this radius is R1. Here we have this formula for finding R. It is the sum of absolute value for all entries in the first row except A11. It says I doesn't equal to J. Okay? Except A11, we find the sum of absolute value for all the other entries. Look at this here for this matrix. For lambda 1, we say lambda 1 is in the circle, in the disk. The center of this disk is A11. Okay? The center of this disk is A11. This is B1 actually. This disk is B1. The center is A11. And the radius, this distance, the radius is from center to the circumference. This radius is absolute value of this plus absolute value of this. Okay? This radius is absolute value of -2 plus absolute value of 1. It is 3. Absolute value of negative 2 is 2. Absolute value of 1 is 1. 2 plus 1 is 2, is 3. So this radius is 3. If the center is 3, how about the circle, the endpoints? This is 6. And this is 0. Is it? Look. We have the circle. The center is 3. If the radius is 3, so what's this point? Of course, it's 0. We go 3 units to left. We subtract 3 from the center. And going to right, we add 3 units to the center. It is 6. This is B1. How about B2? B2, we do the same for this one. B2, just we do that. What's the center? It is A22. For the last one, it is A33. Okay? This is 2. This is 3. Then how about the radius? The radius is the sum of all entries except the one which becomes the center, which is -1 in an absolute value plus 1 in an absolute value, which is 2. Is it? It's 2. So what are these two endpoints? 3 plus 2 is 5. 3 minus 2 is 1. So B2 is a disk at center at 3 and radius is 2. As here radius R2 is -1 plus 1 in these two in an absolute value. In the above one, we said it's absolute value of these two. For the last one, it's absolute value for these two. Okay? Now, for B3. B3, it's the circle. What's the center? The center, we use row 3. It's 3, 3. Okay? It is A33. For B3, the center is A33. For B2, the center is A22. For B1, the center is A1. Okay? This is the center. The entry that we use for the center, we don't use it for the radius. Okay? We don't use it for the radius. Here, the center is -1. How about the radius? You see, R3 is absolute value of 1 plus absolute value of -2, which is 3. Now, -4 plus -4 plus 3 is 1. -4 minus 3 is, so it's -1. This is -7. This is B3. Now, we need to find the region, one region, the union of these regions. We need to find a region which includes these all regions. Okay? The union of these all regions. Now we draw all together. That's it. This is 0. It's 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6. The first one is 0 to 6. And center at 3. From 0 to 6. 1, 2, 3, 4, 5, 6. That's it. It's the first one. And the second. The second is from 1 to 5. Is it? The center is at 3. That's the center. From 1 to 5. That's it. Then the third one, from -7 to -1, the center is at -4, -1, -2, -3, -4. That's it. The center is at the point 1, 2, 3. That's it. We now have all together. And then we find the union of them. The union of them, which is which color should we use? Let's use blue. This one. Oh, sorry. This one is okay. From -7 to what? To 6. Here, when we found this one, the red one, which is B1, means lambda 1 is in that interval. Lambda 1 is from 0 to 7 to 6. That's in that interval. For the second one, which is the black, means lambda 2 is between 1 to 5. Lambda 3 is between -7 to -1. This each of these is a region which an eigenvalue in. Okay, then all the eigenvalues, we could say all the eigenvalues are between -7 to 6. All of them are between these two. So this is the region, which is the eigenvalues. Okay, this is how to find them. That's it. Here it is the circle. S is the region for the eigenvalues of a matrix. It's the union of all regions. Okay? With this one, look. We say, yeah, it's used for drawing the graph, actually. It's used for drawing the graph. The graph could be drawn as I did now. And also it could be drawn by this one here. We say B1 is absolute value of lambda minus AII was 3. Okay? Less than RI is 3. Then lambda minus 3 in an absolute value is less than 3. What we do, we say lambda minus 3 is between -3 and 3. We apply that for absolute value. Then you find lambda. You find the region for lambda. Lambda is between, here we add 3 for 0 to 6. It's what we found before. Okay? But here you should use this in final. Yeah, you should use the formula for in final. If the formula is given, these formulas will be given for the final.
So you don't need to memorize.
You don't need to memorize them. I checked 2 to 3 past year papers in all are given. This one, so it's the union of all regions. So what if this is given or not? Okay, it's the union of all regions. It's the blue one which we drew here. It's the blue one. That's it. Look, lambda is between 0 to 6. For the first row, it depends on the rows. How many rows we have? We must have that number of B. We must have that number of region. And then you find the union of them. That will be the region, which includes all the eigenvalues. Okay? This is for the first one. This is for the second one. First, you should find this and then draw the circle. And then for the third one, -1 to -7. That's it. Then union them all. That's it. This is S, this black one. Yes. S is from -7 to 6. So all eigenvalues are in this region from -7 to 6. That's it's Greenwich-Gurian theorem. in Gregorian theorem, we just need to find a region for the eigenvalues. We find a region for each and union all to get the region for all eigenvalues. So all eigenvalues of this matrix must be between -7 is -7 to 6, must be in this region. Okay, all the eigenvalues for the given matrix are in this region. This is about Gregorian theorem. We have two more methods for next lecture. So